In this video, we're going to discuss independent and dependent events. When we're finished, we'll be able to identify and define those events as well as compute their probabilities. Let's begin with a couple of definitions. Let's define independent event first. An independent event is the outcome of one event that is not affected by the outcome of another event. In other words, let's say that our two events are spinning a spinner and picking a card. No matter what happens to the spinning of the spinner, it doesn't affect what happens when we pick a card. On the other hand, a dependent event is one in which the outcome of the first event affects the outcome of the second. And here's an example for that. We've got a row of flowers in our garden. We pick one flower, and then we pick another one. The second event is affected by the first because when I pick the first flower, then there's one less flower for me to choose from. Therefore, those are dependent events. The easy way to remember whether something is independent or dependent many times just comes down to the fact of whether or not you have more or less options after the first event. If the number of options change, then that is a dependent event. Let's look at an example. In this first example, we have a bag that contains 5 pink, 3 green, 4 orange, and 8 yellow gumballs. We need to find the probability of randomly selecting a green gumball and then a yellow gumball if the first gumball is replaced. Here's what we mean by that. So we reach into our bag and we grab a gumball, and we pull it out the bag. And before we pick another gumball, we put that one back and select some other one at random. The first thing we need to do is decide whether or not these are dependent or independent events. Since I pull my first gumball out and put it back in, the number of gumballs that I get to choose from does not change. That makes this an independent event. I'm just going to make this note. Independent. So now, what it is that we're trying to find is the probability of picking a green and then a yellow. So we're going to write it like this. Probability of a green then yellow. And we're going to find the probability of each one of these things separately. The probability of picking a green gumball is, we have 1, 2, 3 green, which is what we were told in the problem. And total gumballs we have are 5 plus 3 is 8, plus 4 is 12, plus 8 more is 20. So the probability of getting a green gumball is 20. Let's now find the probability of getting a yellow gumball. We know we have 8 yellow gumballs, and because we put our first gumball back in, we still have 20 in our bag. So the probability of a yellow gumball is 8 over 20. Unfortunately, that just gives us the probability of each individual event, and we need to find out what the probability is of pulling the green, putting it back, and then pulling the yellow. So we have to have a way to combine our probabilities. If you will think back to when we learned about how to count all of our possible outcomes, and our fundamental counting principle, what it all basically came down to is multiplying all of our various options together for each task, and that gives us our final answer. We'll do something very similar in doing this. If we want to find the probability of pulling a green, then a yellow, we'll take the probability of each one of those events and multiply it together. If we write this out in this form, it's the probability of the green times the probability of the yellow. So we will have 3 over 20 times 8 over 20, which is 24 over 400. And let's reduce that. We divide top and bottom by 4. That's going to give us 6 over 100, which we can reduce even more to 3 over 50. We've just computed that the probability of pulling a green and then pulling a yellow is 3/50ths, or 6%. Now, we could have taken the time to solve this problem by doing a tree diagram or making a list of our combinations and seeing how many of these would have fit this combination and done that probability. But as you can see, we would have ended up with 400 different possibilities, and I know it's 400 because that's what my denominator is here. 400 different possibilities to make that list, and that would have gotten quite cumbersome. Good chance we would have missed out on some. So knowing that we just multiply the two probabilities eliminates that problem for us. Let's look at another example. Now we have a bag, and in that bag we have 8 cards, numbered 1 through 8. And in this particular situation, we reach in, we randomly take a card out of the bag, and we leave it out the bag, and we reach into the bag and randomly pull another one. And we have to find the probability that both cards are greater than 5. Well, let's put both of these cards back in our bag so that we can work through this. Because we pulled a card out the bag and left it out, we changed the number of possibilities for the second event. That makes these dependent events. We still do our probability the same way. We're just changing the number of possible outcomes when we do that. So let's put our card back in the bag as we figure out exactly what to do this. So the probability that both are greater than 5, which means we have two different possibilities. The first event is probability greater than 5 times the probability that is greater than 5. The first time we pick a card, and let's just randomly pick one, we have 1, 2, 3 cards that are greater than 5. Out of 8 total cards. So the probability of our first one being greater than 5 is 3 over 8. Now let's pull that card out. So let's just pull any one of those. We're not going to put that card back in. Now we're going to reach in and pick another card. And when we look at what we've only got 1, 2 cards now left in the bag that are greater than 5. So we'll pull one of those out. we had two possibilities, and we had, before we pulled this 7 out, we had 1, 2, 3, 4, 5, 6, 7 total cards in our bag when we pulled one out. You can see that the differences here, we're still computing our probability the same way, we just changed our possibilities because we didn't replace it. And that's the only thing that makes it a dependent event. It doesn't change how we compute it. We still have our two possibilities for our probabilities, 3 out of 8. We pull one out, so we got one less card as a 7, and one less possibility here, so it's 2. We want to multiply this out, and we get 6 over 56, which will reduce to 3 over 28. So the possibility of reaching into a bag, pulling out two cards that are greater than 5, if we don't replace the first card, is 3 out of 28. For the final things we want to look at a few examples of some problems and just determine if these are independent or dependent events. Our first example is Lewis choosing one card from a deck, then choosing a second card without replacing the first. Is this dependent or independent? Let's think about this. If you don't put the card back in, then you have changed the number of possibilities. You have affected the outcome. So that makes this a dependent event. Let's look at a second example. Adriana picks a flower out of a big bouquet. She doesn't like the one that she's picked, so she puts it back and picks another. As we consider this, when Adriana goes to pick the second flower, she's got the same number of choices as she did the first time. It was unaffected, so this is an independent event. It is unaffected. For our final example, we've got Ivy's mom laying out her clothes for her. She lays out 6 shirts, 4 skirts. Ivy gets to choose from them. She picks a shirt at random, picks a skirt at random. Unless you're worried about them matching, which we don't have any indication that that's the situation here, she's just randomly picking a shirt and then randomly picking a skirt. Well, the number of skirt options available to her doesn't change when she picks a shirt, because she doesn't care how she matches. She's making her fashion statement this way. So one is not affecting the other. Therefore, these are independent events. One is not affecting the other. So that sums up our very brief discussion of independent versus dependent events. The key thing to remember here is that if you affect the number of choices, then you suddenly have created dependent events. The other thing to keep in mind is that when we're finding the probabilities of these compound events, more than one thing happening, what we're really doing is multiplying the probability of each individual segment to get our total probability.